next talk is by David Rottensteiner, also from Ghent University, about the harmonic oscillator on the Heisenberg group.
Okay, thank you very much. So the title of my poster is The Harmonic Oscillator on the Heisenberg group. This is based on joint work with Michael Różański. It's based on a short paper which is going to appear in Compte Rendu. And this again is say a shorter version of a longer paper which is under review, which is called Harmonic and Anharmonic Oscillators on the Heisenberg group. So, sorry. So what's our goal here? So Michael and I found out that there is actually a natural. Sorry. Okay. That there is a natural analog of harmonic oscillator in the Heisenberg group, which serves as a canonical analog to the one on Rn. Our approach is based on a few assumptions, which few insights that we have on Rn, or say well-known facts about the classical harmonic oscillator. First of all, so the one on Rn can be written as a negative sum of squares of relatively simple operators related to the negative Laplacian and the quadratic potential. It can be written as the violent Koenig quantizations of this quadratic symbol. And moreover, it's the image of the negative sublaplacian on the Heisenberg group under the infinitesimal Schrödinger representation of the Heisenberg group. And this is related to the fact that the Heisenberg group is a supergroup given as the semi-direct product of Rn acting on itself. So we're going to follow a recipe which somehow emulates these facts. So there is a group which was originally studied by Dinin and later in more detail by Folland, which is why we called it the Dinin-Folland group. It's a semi-direct product of the Heisenberg group acting on Rn. And one can study its unitary irreducible representations, either by Kirillov's Orit method or by hands-on approach. And then the generic ones can be described by Heisenberg translations and the classical modulations or frequency shifts. And then if we consider, so this is a three-step nilpotent group, which is stratified, so in particular it's homogeneous. And if we consider, say, a standard basis, which describes the Lie algebra, and take a sum of squares of the vectors in the first stratum, then we get a natural sublaplacian. So if we take the infinitesimal representation of that group, or of the Lie algebra, sorry, and look at the image of this negative sublaplacian, then we get an operator, which is essentially self-adjoint and whose domain lies inside L2 of Hn. And the domain in particular includes the smooth vectors of that representation, which are precisely the Schwarz functions. It can be interpreted in the following way. First of all, it's again a differential operator given as a sum of squares of a negative sublaplacian in this case and a quadratic potential. It's given again as Dinin's Weil quantization of Euclidean, of a scalar value, the quadratic symbol, as the Koenig quantization in the sense of Fischer and Różański of an operator valued symbol, again in the same variables, and by definition as the infinitesimal representation of a negative sublaplacian. And now what's our main result? So this is the operator on the explicit formula for H1, that is on R3. And our main result is the following. This operator, this harmonic oscillator, has purely discrete spectrum. Sorry, probably Michael's face is covering this now. Has purely discrete spectrum inside 0 infinity. The number of its eigenvalues counted with multiplicities, which are less or equal a certain threshold lambda, is asymptotically given by lambda to the 6n plus 3 over 1/2. Over 2, sorry, I will say what that means. And moreover, the eigenvectors of that operator are Schwarz functions, and they form an orthonormal basis of L2. So very much an analogy to the classical harmonic oscillator. And then maybe I say something about this, the growth of the eigenvalues. So this power is intimately related to the homogeneous structure of this Dinin-Folland Lie algebra. Namely, the denominator is precisely the homogeneous dimension of the first two strata, and the denominator 2 is the homogeneous degree of the negative sublaplacian on the Dinen-Follin group. Here there's a list of references which we used. And if anyone's interested about proof methods, I can say a few words about that. Thank you.
Okay, thank you very much. Any quick questions?